Hello everyone, welcome to my channel. Today we're going to be solving a Rosalind problem. This is going to be number 1 in Bioinformatics Stronghold with the ID DNA. The problem itself is called counting DNA nucleotides, and if you'd like to try it yourself, I'll have it linked in my description below. Let's first try to understand the logic of this problem before we code it in Python. What the problem gives us is this string of nucleotides, and what nucleotides are these bases A, T, C, and G, and they make up DNA. It's adenine, thymine, cytosine, guanine. This is going to make up most of the genetic data that we work with in Rosalind. So we also know that the string given to us is going to be called S, and S is never going to be more than 1,000 nucleotides long in this specific problem. We're not going to focus too much on this aspect, but it is important to note that since genetic data will usually be much larger than this, we are going to try to focus on methods that will reduce space and time complexity. It also states in the problem that we'd like to count how many times each nucleotide occurs in the string S, and specifically what it asks is how many times A, and then C, and then G, and then T. We're going to have to output in this specific order, so we also have to focus on that when it comes to this problem. One thing we can do is brute force it, where we would say, okay, so for each character in the string, we're going to check, is it A, G, C, or T? And that would require checking each of the letters prior to adding them to a counted list or a dictionary, or whatever data type that we end up choosing to store these numbers in. The important part is that after we count all of these values, we're going to have to output it to the screen in this specific order. So if we just go ahead and use this sample string, if you just count them manually, you can see that A is going to have 20, C has 12, G has 17, and T has 21. So eventually we're going to print these values however we store them. And that's going to give you a pass on this solution. So let's get into coding it. I'm going to show you several different ways to solve this problem, as well as the corresponding time and space complexity for each solution. They're all going to be time complexity O of n and space complexity O of 1, but I'm going to explain the differences between each because there's going to be differences depending on the genetic data you want to work with. First, we're going to work with the data that they gave us, so that's going to be this string that I'll just copy and paste in here. And you know, this string is short enough, you might be able to read it and just be like, okay, there's like 20 A's, whatever. But we're not going to do that because guess what? The file is going to be super long. The first method I have is to actually use a built-in function, which is going to be called count, and we'll also just print it out to the terminal since we don't need to store any values. Working with genetic data, you're going to actually have to do throughput data, which basically means that you're not going to store the majority of the data that you're going through. You're just going to parse through it and then print it to terminal, but you're not going to actually store it in your code, and that's how you're going to keep your code a reasonable size and speed. Now that we have all the code we could ever need for this problem, we're going to go to the terminal and run it. And how you're going to do this is you're going to type Python and then the name of your file that you have this information in. And since we put it in order that we wanted to count A, then C, then G, then T, we do have the expected output, and it would work if we put it into the Rosalind problem. Since that was just a sample, we're going to use the actual text file that they had given us, which is called Rosalind_DNA.txt. And as you can see, this is slightly longer than the sample we were given, which is why you can't just brute force, count each one by your hand, and then, output it like this. You just can't do that. It's terrible. So we're going to edit this. We're not going to hard code the string anymore. We're going to actually open the file, and how you could do this is with open, the name of the file, as file. And this is super easy. You just do this most of the time when you have a file to open, and depending on the extension you're going to probably change this, but most of the time it should just be file. And what we're going to do is file, which is the object that we are trying to read from, dot readline, and readline simply reads this line. It just goes through and it's like, okay, this exists. And then we're going to do dot strip, which should remove any trailing white space, which is just extra space at the end of a character, just like this. It's good practice to close your file after you've used it, but this is going to be negligible in this case. After that, we try again, and we get the amounts that are in this DNA file. This is going to be the fastest solution for small to medium files because we're not creating any Python objects to store anything except for s, which is storing the string that we read into the file. .count is not storing anything, it actually just goes into memory and retrieves the count for each. It just does some stuff under the hood, and it's able to retrieve the counts faster than if we were going to store each of these counts in a dictionary, a list, or use a for loop. Technically, this does do 4 passes over the data. It doesn't just do 1 because of one print statement. It counts 4 times, but because it is a C-level process, it's going to be faster than storing a Python object like we would otherwise. Moving on to the second solution, we're going to be using a for loop and a dictionary, which is probably one of the most common solutions. It was one of the first solutions that I came up with, and it's very simple and easy to understand. Since we're going to just be working with this Rosalind DNA.txt file, we're going to keep the same format as the first solution where we use with open as file. We do read line and then we strip it of any white space. For this solution, I'm going to be using a dictionary. We're just going to call it counts since all we are storing is the counts for each nucleotide base in the string. And we're going to assign each one to 0 since we're going to increment every single time we see it in the string. And once again, we're going to be going in the order that Rosalind requested. So we're doing A, C, G, and then T. And that's the end of that dictionary. And then we're going to do a for loop for each base in the string S. We want to check if the base is in the counts dictionary. What this does is it goes over this entire string and it's like, okay, for this letter, for the base, is this in the dictionary? Is it one of the valid letters? And if it is, then we are going to do the key. So we are doing the base. So base is going to be one of these letters, like from the file. We are using that to access the value. And then we're going to increment by 1. Plus equals 1 just does, like adds 1 to the count. And we don't really need an else statement, just do nothing if it's an invalid base, but most of the time it should not be. And then we're going to just do that print statement again, but this time no s.counts because we're not using the built-in function. We're actually going to go into our dictionary counts, which is a Python object that we've created. That's what makes this solution a bit slower than the last one because this is a Python method, and when we were doing .count, it's actually it's built into Python, I believe using C. Make sure this print statement is not tabbed in because if you tab it in, it's going to print like 1,000,000 times. So now that our code is finished, we're going to run it again using that same command earlier, python dna.py, and it gives us the same exact values as before, making this a valid solution. This solution is also time complexity O of n, but it's slightly slower than the first solution because we are using a lookup for a hash map. Python objects generally take more time than a built-in C object or under the hood object from C. C accesses memory, whereas right now we created these objects to access, which makes it slightly slower than the first solution, but it's still a time of O of n. Space complexity is also just O of n. To summarize, the first method, I used built-in counts where each call scanned the string in a single pass under the hood in C-level programming. So even with the 4 scans that we did using .count, it was the fastest solution. And then the second solution is something that is more beginner-friendly, where we use a for loop and it goes over each base, and we stored each value in a dictionary, which could be useful for bigger projects where you're using more important genetic data than just one single string. I hope this helped, and if you have any questions, comments, concerns, criticisms, just let me know in the comments and I'll reply as soon as I can. Thank you so much and have an amazing day.